Alrighty, I'm just about ready to start if y'all are set up. Okie dokie. Can I ask y'all to go ahead and mute until you have questions, and then feel free to unmute at any time. Feel free to interrupt me at any time. As a matter of fact, I beg you to please stop me if anything I've said is confusing or not clear. I have done this for a while, so some things I take for granted, and it's just because I got familiar with them. So if I make a jump that doesn't make sense or anything like that, just stop me, get me to rephrase it, just go ahead and interrupt me, because this is for you guys. So with that, I guess we can go ahead and start. So I am recording this. I will post it on YouTube. It'll probably go up late tonight, like midnight. So don't expect the link and this to be processed until, tomorrow morning at the earliest. Let's see. So I'm probably going to cap this at like 8 o'clock, unless we either are really close to done or we got some really, really good engagement. Hello, welcome. Please mute yourself until you are ready to ask questions and stuff. Let's see. I'm not recording your side of it at all. And you're all welcome to use the office hours text chat to ask questions. I'm going to be checking on it periodically, but I have one monitor, so I may miss some stuff. So I'll try and handle things as soon as I can. Let's see. So this is going to be conceptual. I don't have any problems prepared, and I don't plan on live solving anything. But if you have questions, like specific questions you need help with, go ahead and shoot them to me, and I will give you the necessary concepts and strategies, tactics to kind of get through them. Let's see. And this is the whole class. The content I'm going to go over is basically the whole class. I'm not going to tell you what's going to be on the exam, other than it's not technically cumulative, so anything after exam 1 is is possible. That being said, you're not going to be tested on the extra credit assignment. That was just stuff that Dr. Doss and I really thought that you should see once before you leave electrical forever, or have to run into it in senior design, which is what happened to me. So with that, do we have any questions before I go ahead and dive into 11 pages of notes? All right. I will take your silence as a no questions, and we'll go ahead and get started. So I kind of want to start with the core basic stuff from the beginning of the class. So we're going to look at just circuits. Probably feels really stupid to be defining circuits this late into the class, but a circuit's really just a closed loop. Like, if you're running a circuit, it's literally it's the same concept. It's just a closed loop of some conductive thing. Usually it's wire. If you stick your tongue on the 2 prongs of a 9-volt battery, you have become the wire. But overall, circuit's just a conductive thing in which electrons can move. So basically, without trying to, I don't want to get too deep into the atomic model stuff, but basically, atoms bond at the outermost electron, and that is the thing that moves. When atoms bond, this electron's kind of shared between both of them, so it can move freely anywhere. And so when you have like a wire which is bajillions of copper atoms bonded together, you can have this electron go for miles. And that's literally just what's happening in the wire, is electrons are moving. Hello, welcome. Please mute yourself until you have a question to ask, and then please, by all means, interrupt me. So, this electron, so we think about the electron, or the current, as moving in the opposite direction as the electrons move. So, when you have some positive negative source, we think about the current going this way. The electrons are pushing out of the negative side, basically. So that's not really necessary for this class, but it's good to kind of have a concept of it. But all you really need to really understand is that electrons are moving around wires, and that's what current is. And that kind of brings us to just Ohm's Law and how we do math in circuits. So, we have some voltage source, and we're all working in DC right now. You can think about DC as like a snapshot of alternating current, and that just let that percolate in the back of your head, because you can do everything you can do in DC and AC. They're the same thing. So, you've got this really simple circuit. This voltage source has a voltage. That voltage pushes current. So there's a current going around, and we generally have a clockwise convention. So we just assume that current comes out of the positive, and we assume that current goes clockwise. If you have a really rude problem that does this to you, go with the current goes out of positive, and write your current going this way. But in general, clockwise, nice things happen when you don't have to deal with negatives, so we'll use the positive side. And then this is a resistor. And this is basically this is what everything boils down to in electrical engineering. This is Ohm's Law. And Ohm's Law just relates this voltage source, this current, and whatever resistance you have. It says that voltage is the current times the resistance. And that is very useful because you can mix it around. It's a law. It's always true, which means you can rely on it. You can do funny things with it. So, practically speaking, this resistor is a toaster. It's my computer. It's the LED that I have on my lamp. It's anything that you could plug in. It's the motors inside a Furby. And the voltage source is the 17 AA batteries you have to put into a Furby. This circuit is, it's just a diagram. It is a simplification of what's really out there. So that means you can draw it however you want. If you want to draw this same circuit like this, these are equivalent, assuming that this voltage source and this resistance are the same as up here. It's anarchy. Do whatever you want, just make sure it's clean. And make sure it's clean is just there so that you don't misread your chicken scratch at 2 a.m. because that hasn't happened to me before. Nope. So, we know from Ohm's Law, and yeah, I'm gonna rewrite a lot of stuff. We know from Ohm's Law that voltage, current, and resistance are all related. But from that, we can figure out that power is also related to these things. So, we first meet power and work and energy in physics, and we meet it in Newtonian physics. So we meet it as like a ball rolls and that kind of stuff. It's got a very, very easily imaginable relationship with our physical world. And I mean, I don't know about you, boss, but I can't see electrons. I can't break open this wire and see the electrons pouring through it. There's not a good way to describe it. So I'm gonna do my best, and if this becomes very confusing, just stop me. So basically, we can kind of think of this electron as the energy source. This would be like if you were talking about potential energy and you raised this ball 7 feet in the air. This ball now has potential energy. Because it could fall. And the sheer act of it just falling means it has energy, and it is using that energy. So up here it has potential energy, and if it were moving, it has kinetic energy. Well, we can kind of talk about electricity as having electrical potential energy. And as a matter of fact, voltage is kind of also referred to as electric potential. It's basically, this is the thing that lets us do stuff at all in electrical engineering. It's the electrons. It's where it's where the potential for stuff to happen comes from. And I know that we just talked about power, and then we're starting with energy, and it's because these things have a derivative relationship, and I mean that in the mathematical sense of the word. So power is the derivative of work with respect, and this is electrical, so electric power. Electric power has the potential, or has a derivative relationship with work. It is the change, because D means change. It is the change in work with respect to the change in charge. And this should technically be the big Q, because little q is the elementary charge. Work is the force applied to create displacement, and that's easier to think of in ball terms. So work is what it took to get this ball 7 feet in the air. Well, for electricity, work is what it takes to push the electrons around the wire. It's not the speed at which it goes. It is what it takes to make it happen. So you can think about that as the voltage. Because the voltage, like we said up here, pushes the current around the circuit. So power has this derivative relationship with the work that voltage does. Voltage is the change in work with relationship to the change in current. But power is work with relationship to time. So if we say take then dq over dt, which is current, so I'm gonna redraw this because that makes it look like voltage is the whole thing, and that's not true. So this is a property of derivatives. If you line them up like this, you can cancel these just like they're fractions, because they're kind of fractions. So what you get is the change in work with respect to the change in time, which we know is the definition of power. We learned that from Newtonian physics. And honestly, everything in Newtonian physics has a parallel in other specific fields. So we talk about voltage as being a work analog. We talk about current as being, or we talk about charge as being an energy analog. And so we can find power of a definition that we know exists in terms of the specific field, and that is how we get power equals V times I, because the relationships dictate this, basically. So you're gonna find that everything in electrical, and basically anything in engineering ever, everything is relationships. Alright, so just gonna check on chat real quick. Alright, so are there any questions so far? Alrighty. So what can we do with this? Because honestly, this is definition stuff. And I guess I'll go ahead and just rewrite it cleanly here. So Ohm's Law, V equals IR. And from that we get power is VI. And you usually don't need the derivative forms. Largely, especially, so in DC especially, you can just use these point forms. You don't usually need the derivative forms. However, in AC, you probably do. And that is because, basically, in direct current, you're working with a steady voltage, a steady current, a steady resistance. And this means that you will have a steady power. So there's only one value for these, and the values are not expected to be continuous. In AC, in alternating current, because everything is based off of the sine wave, we expect it to change continuously. So we do need to think about these in terms of their function as opposed to a specific value. So in AC, you usually do need the derivative forms. And again, derivative forms, I literally mean the derivatives that define them. So I'll go ahead and write it here too. It is dW by dQ. No. By dQ dt, such that dW over d dt. There we go. So go ahead and write that down. let's see here. Sorry, I'm messing with my desktop. Just try and rearrange things a little bit. Alright, so that being said, we need to be able to do more stuff with the laws that undermine, or not undermine, but like hold up electrical engineering. Because, let's face it, this is not a realistic circuit. I can make that on a breadboard and that will work. But what does it do? Because you don't know what this resistor is. If this resistor's one of these boys, then this circuit just happens and there's no output. And by output, I mean you don't see anything on the outside. There's no light that happens, there's no motor that runs. It just happens. And I mean you could put a voltmeter on it and you could tell that stuff's happening, or you could put a amp meter in line with it and see that current's happening. But like this isn't a practical circuit. These things usually have bars on them that tell you how big they are. But like we need to be able to do stuff, and we need to be able to look at more complicated circuits. So that's what Kirkhofs laws give us. Kirkhofs laws give us. There we go. So Kirchhoff had two really big brain laws, and they are like the next biggest thing next to Ohm's Law, because they derive from Ohm's Law, but like everything else, if you combine Kirchhoff's laws and Ohm's Law, you can do anything. You can do anything. It might not be easy and it might not be fun, but you can do it. So here they are. The first we're going to look at is current law. So basically, this guy said, well, hey, if we believe in conservation, which is the Newtonian physics thing of energy cannot be created or destroyed, and neither can matter, it can only change form. If we believe that in our heart of hearts, then the same goes for electricity, because those electrons ain't going nowhere. And unless you're doing quantum physics, which I know you are not doing quantum physics, those electrons obey this. Those electrons ain't going nowhere. So basically, the idea is, whatever you put in, you get out. If you put in 3 currents, and you're only getting 1 out, well, that 1 out equals both of those currents. It's conservation. So, if we label this I1 and I2 and I3, then we can say that I1 plus I2 minus I3 equals 0. And I'm writing it this way because this is the way that you're going to solve with it. Because the other way to put conservation is that the sum of all currents going in or out of the node is 0. And that's how we're going to write it. The sum of all currents going in or out of, and I'm going to write any given point. Any given point in a circuit is 0. You can write that as sigma currents equals 0. Sigma being the sum of all currents. However, I'm also just gonna write it the nice way of I1 plus I2 minus I3 equals 0. So this is a convention. The fact that we made I1 and I2 positive and I3 negative is a convention. We have basically just asserted that all I going in are positive and all I going out are negative. You can assert the opposite, but you have to keep it straight. If you're gonna do it, you have to go all in. You have to make all going in negative and all going out positive. If you don't, then it's not gonna come out correctly. We use these conventions because having something pre-said and like pre-decided when we start just makes it easier on the back end, so that all you have to do is just chug through the math and be done with it. You don't have to decide, well, for this problem I'm gonna do it this way or that way. We'll just deal with the ramifications on the back end. So unless you're super comfortable, I don't suggest changing the conventions. However, if you are super comfortable, go ahead, do whatever you want. If you feel good with the relationships, again, everything is relationships. So we're gonna look at just some whatever circuit that I decide to make, and I can make some really ugly ones. Because I want to point out what constitutes a node. And why I decided that I should phrase it up here as any given point. Because this is a given point, and the current going here has to equal the current going here. That's conservation. However, this point is not a node. And this is just a piece of wire, because this is just a piece of wire. And in 292, we don't give a resistance to wire. We are assuming ideal wire, which means that it has no resistance, and therefore it transmits 100% of the current. Now, if you go up to the power systems class, wire has a resistance, and you're just, it's not going to be fun. It's just not fun. But it's there, and it's realistic. If you run like 6 feet of copper wire between a 9-volt battery and a light bulb and back, you are going to get a dim frickin' light bulb, because that battery cannot push enough current to light up the light bulb to full capacity across 9 feet of wire. But that's the real world, and we don't have to deal with that right now. We are learning the basics, and so we are just going to simplify it until we can say with confidence what we're doing. And so if this is not a node, we do need to know what are nodes. So this is a node. This is a node not because this is empty wire and it has 3 sprigs. It is a node because there are 1, 2, 3, at least, circuit elements all attached to the same point. And I'd group these together because they're in series and you can just add them. This is just one slightly larger resistor. So this is a node. Well, okay, this is also a node. However, you're not going to get the current off of this. You're not going to be able to calculate it. And that is because we have assumed ideal sources as well. And ideal sources have no resistance. So we can't tell you what this current is, but we do know that it has one. And we also have current here and there. So that is a thing. I would suggest mesh analysis with this one, but we'll talk about that later. So that is current law. Basically, all you do is you say, okay, well, this is my node. This is node A. At node A, we have some voltage A. We have some voltage B, and actually that voltage B, because this is ideal and because this wire is ideal, that voltage B is actually equal to our source. The source. So we don't have to, for node analysis, we don't have to think about what VB is. We just get to do it. So all we have to analyze here is node A. And at node A, we have some current A, some current B, and some current C. IA, IB, IC. And, well, we're going to find the sum occurrence there. So we're going to say I equals IA plus IB minus IC. Shway. So, how do we do anything with that? So, this is the part that kind of gets confusing in the brain space. We're going to get this in terms of voltages. Thus, why we call the node analysis node voltage analysis. However, node voltage analysis works with Kirchhoffs' current law. Now that's backwards, right? So we're just going to note that over here. Node voltage analysis uses Kirchhoffs' current law. Yeah. Okay. So we're going to write these in terms of their voltages because we can figure out the voltages. We do that because we were given the source, and this source is like 72.5 or 7.25 because that's what I actually wrote. Volts. It's something. It's a number. It is a number. At least in DC. In AC, it's probably a function. But that's okay. That function is a number. It's just a lot of numbers. It describes a set of numbers. I won't dive into that deeper because I'm just going to confuse people. So this voltage is a number. We were given it. So we have a shot in the dark of figuring out the other voltages in this circuit. I mean, we already figured out VB, right? We figured out VB just by the characteristic of the circuit and the assumptions we made, the ideal assumptions we made. That VB is the source. So this one's also 7.25 volts. So all we have to do is find one more voltage. And then we're done. Then we understand what this circuit means. Or at least what is happening in this circuit. So we're going to write these in terms of their voltages. And we're going to do that, and I know that this is a little bit backwards from the way Dr. Doss presented it, or at least I've been told that a couple of times over the course of the semester. So if you feel like this is not the way to do it, don't do it this way. But this way will work. So we're going to start, and we're going to consider ourselves anchored at A. So we're going to say IA is... Why am I not writing? Oh, now it's writing. Okay. Fun. We're going to say IA is VA minus because we're going across the element backwards, by the way. because we standard write all of our elements like this, or like this, with the positive terminal up and the positive terminal to the right, left, unless it's already stated in the problem. So this one's going to be VA minus VB over this resistor. We're just going to call it R1 or RA. So VB over RA. And then we're going to do the same thing for VB. Well, okay, so cool. What is this voltage? Well, we're going to look at our source. If this is a negative sign, then I can just put the ground symbol anywhere down here. Anywhere down here. And it's grounded. I mean, I guess I wouldn't put it here because that does change the circuit. But like, anywhere there's a blank wire on the underside of the circuit, assuming the underside of the circuit is the negative end of the voltage source, yeah, you can just ground it. Just consider it 0. Because that's what ground is. Ground is 0. So we've got VB minus nothing over RB. And then we've got IC. Well, IC is a little less pleasant because it's going to be whatever RC1 and RC2 are. And we're going to call that REQ. Because we can do that. Because resistors in series, you can simply add. To find an equivalent resistance. So, what we're going to do is we're going to say this is VB minus... Aw, shucks. Well, okay, this one also goes to 0, right? So, VB over 0 over REQ. And we can say that REQ equals RC1 plus RC2. Alright. So, let's see here. So, I just got a question about Discord. So if my camera is not the dominant view, then you should be able to choose an option that says hide, that basically hides all the other, the non-camera sharing members. Let me see if I can figure out how to do that for you real quick. So if you click into the call, you should hit the 3 dots that says more, and then unselect the show non-video participants, and that'll make my screen the only one you see. Okay, hopefully that helps. I apologize for that. I should have asked people to set that up earlier. Alrighty. So, this is it. Since we have a value for VB, we'll just plug that in. And we have all the values for the resistors, so we'll just plug those in. So all we have to do is rearrange this through algebra to find VA, and we're done. That's it. That is probably the most direct answer to current law. So we're gonna now look at the other one, voltage law. So voltage law is also based in conservation. Conservation of this one is around the circuit. So we've got this circuit, random circuit. And what we're saying is around a circuit, so around a loop, the voltage adds to 0. Hello, welcome. Please mute yourself, and unless you have a question, also make sure that you unselect the show non-camera participants. Alright, so we're looking at just a loop, but we're gonna have to look at all the loops, especially if there's an element being shared. If this was just shorted, so I'm gonna draw kind of a smooth brain circuit, and I say that because if someone did this, it would be very, very pointless. So current takes the path of least resistance, and you might have heard that phrase before. You might have heard that phrase in relation to water, because water also takes the path of least resistance. It's because it's easier. It's because it costs less energy, and systems... It's bad to characterize it as desire, because it's not like the system has, like, thoughts of its own, but, like, because of the way energy works, all sorts of systems will seek a stable state that costs the least energy. And let me tell you, going through a bunch of 300 ohm resistors is not a little amount of energy. But this wire, especially this ideal wire, whoo, that is easy sailing. So electricity's gonna go like this, and just ignore this. But, bright side of that is you actually only have to analyze this loop with voltage law, because this is the only one that's doing anything. But voltage law says that the sum of voltages around a closed loop, not that an open loop would transmit any power, but the sum of voltages around a closed loop adds to 0. So, the sum of voltages around a closed loop is 0. Sweet. So that's something else we can rely on, because it's based in conservation. It's based in a law that we already know is true. So what we do is we draw a current loop. Alright, so this is voltage law, and we draw a current. Yeah, these things are not, they're not intuitive. They voltage analysis? Equals current loop. Current mesh. Yeah, it's confusing, and it's just kind of the way it is. So what we do when we look at voltage law and we analyze, we do mesh analysis, is we follow this current around this loop. We've asserted that this current's going to be the same, and we can do that because we've said that the voltages all add to 0. And well, these resistors aren't changing, and that voltage, even if it was an alternating current, it's not changing because we know how it's behaving. So it's not going to throw us a curveball and leave us a mystery. We can rely on it. So we are going to. We're going to follow this around, and again, clockwise is a convention. You can draw it backwards. Just make sure you keep it straight. keep all of your relationships straight and you can do whatever you want. So, we know that we also have this convention. It's gonna do the thing again, huh? Come on. Remember how to draw. Okay. Oh, it's because I'm on the eraser. I'm a dingus. Okay. So we have this convention where we draw voltage as the front side and voltage as the top, or positive voltage as the front and positive voltage as the top of elements. And this matters. This is another convention. This especially matters with our clockwise convention. So what we're going to do is we're going to just find the voltages. And we know that there's a voltage across this resistor. Not just because we mechanically know, or we academically know that resistors have voltage drop. What does that mean? That means that this resistor is eating some of the voltage. This is one of the things that is preventing the full power of this little voltage source from totaling this circuit. Resistors are useful because they make sure you don't kill, say, an expensive Texas Instruments chip in a breadboard circuit. Ask me how I know that. But they are impeding, and that'll be that you know where I'm going with that. They're impeding the flow of current. And so to get past that, some of the voltage kind of gets defeated along the way. So we know that there's a voltage here. We know that this device, this resistor, costs voltage to have current go through it. But we also know that there is a very specific and consistent relationship between voltage, resistance, and current. So we're going to start here. This arrow's pointing clockwise, and if we follow it clockwise, it hits the positive terminal of this resistor, and we're going to call it R1. So we're going to write that. R1. That's the voltage here. And then we're going to follow it down. And, well, so this one's a funny one, because this one is actually sharing I2's current. Because this, so there's not two currents going through this device. This device feels one current. But, oops, I drew that backwards. Convention. Keep our convention straight. This, however, the current that this experiences is going to be the sum of these two currents that we've asserted exist. So we're going to say R2 plus R2 times, well, okay, so I goes into the positive terminal, so it's going to be plus I, and then I2 goes into the, I2 goes into the negative terminal, so it's going to be minus I2 equals 0. That's a lie. You know why? Because we have a voltage source. And that voltage source is just some V. And, well, we're coming in to the negative terminal. So we're going to have minus Vs equals 0. And then you're going to write the same circuit on the other side. Or, you know, the same kind of equation on the other side. So we've got R3 and R4, and we've got, well, this shared R2. So we're gonna let's start with R3 because it's less bad. So R3, we're gonna go into the positive side. So we're gonna have I2 R3 plus I2 R4, and now we have to deal with R2. So we know it's going to be R2 because the resistance hasn't changed. And, well, we're gonna say minus I2 plus I1. And you'll note that these are in the same order. Or more, these are the same term. This minus I2 plus 1 and this plus 1 minus I2, they're the same thing because transitive property of addition. And so, and that should be a gut check for you, because the difference is gonna be the same. This current isn't changing just because you're looking at a different loop, because this element connects these two loops. This is the thing that relates I1 and I2, and also means that you have to actually look at I2. So then from there you plug in what you know, you solve for, you can probably get away with solving for one and then the other, because, let's see, so you're given Vs, you'll be given all the resistors, so then you'll be able to solve one of these in terms of I1 and then plug it in, or you can use a matrix. If you end up with like 6 billion current loops, use a matrix, I implore you. Here's how you set that up. You say that you have I1, I2, ... times, and then current equation 1, where you have the coefficient of I1, the coefficient of I2, ... this way. But you only put the numbers in this side. So for here, we got R2 plus R1. Yeah. And then you have just R2. No, you have minus R2. And, well, what do you do with constants? Well, you're gonna subtract them across to the other side. So this one, you're gonna add. So this one's gonna have Vs. And for equation 2, you're gonna have, let's see, I1 we have R2. And I2 we have R3 plus R4 minus R2. And you don't have a constant, so we're going to make it 0. And this is what you plug into your matrix solver. I firmly suggest you find a matrix solver. Desmos will do it, and also Wolfram Alpha. If you are very, very excited about calculators, your TI-84 will do it, or if you are very, very desperate in an exam that is not at home. It works, but it is not fun. So that is mesh analysis. So this one, I will go ahead and kind of summarize this. So Kirkhofs laws are based in conservation. Current law sum of currents, sum of I in and out of a point or node equals 0. Used in node voltage analysis. Sometimes only called node analysis. It is called node voltage analysis because you are going to get the node voltages out of it. It is not because you are adding up the node voltages. I would like to have some words with the people who named this stuff. Alright, and voltage law. Sum of voltage around a closed loop equals 0. Used in mesh analysis or current mesh analysis. Basically, you will find currents. Yeah. And this one, you will find voltages. Alright, so, any questions about that? Alright. Alright, and if y'all want to DM me questions as well, that's just fine. Either one is easy enough for me to see stuff. Oh, no voice chat. Ah, thank you, Gustavo. That helps. So double-clicking my screen will also focus my, make my screen the biggest one. Alright. So, with that, that's kind of the core stuff from pre-exam, or from up to exam 1 that I really wanted to cover, because I saw some confusion during the exam, and I know how brains can get in exams, so I just wanted to make sure that we cemented that relationship a little better. Alright, so I am now gonna go into the post-exam 1 stuff. This is the stuff you're actually gonna be questioned about. You're still gonna need Kirkhofs laws, you're still gonna need Ohm's law, and the basic understanding that electrons move. That's, yeah, you know. From here on out, this is the stuff that you're probably here for. And we've got pretty much 2 hours on the dot to do it in. If we need a little more time, that's probably okay, but that'll depend on how everyone's feeling, including me. Alright, so from here on out, exam 2 stuff. And I know exam 2 is your final, but... Alright. So, this is where we learned about capacitors and inductors. We got 2 fancy new toys to play with in circuits, and frankly, they're not very friendly. So we are actually going to look at a little bit of atomic physics to get our heads around capacitors and inductors. I probably should have, but I didn't read your lectures or what Dr. Doss covered on them. So, sorry if this is either way out of left field or really, really repetitive. Alright, so this is a capacitor. Well, not really. I mean, the capacitor, if you squint, kind of looks like that, but honestly, a capacitor looks like this if you're looking at breadboard stuff. It's a really cryptic looking little block of plastic with wires sticking out. And that's not super, super helpful. But guess what? You have seen this kind of capacitor. That's a AA battery. Or a AAA battery. They're pretty much the same. And you hook it up and there you go. A capacitor stores charge. So let's go ahead and just start by writing that. Please stop. Please use the thingy. There we go. A capacitor stores charge. What does that mean? Because what is charge? Charge in physics is the how much coulombs is on a thing. Yeah. So what this means is it is packing electrons into something. So this is a metal plate. And this is another metal plate. And these are the wires. And on the inside, there's something we call a dielectric. Dielectric, don't ask me the origin of that word. I do not know it. But a dielectric is something that is not conductive. D-U-C-T-I-V-E, there we go. Is not conductive. Well, oh boy. How are we going to put what's effectively an insulator into something that we want electricity to move through and expect it to move? Well, so that is a property of insulators versus conductors. And that is a property of the atom. So this material, it'll make sense in just a second. So when we're looking at, say, just a hunk of copper, this is copper. This is what your wires are made out of. It's solid. It's of uncertain size. And if you run a wire to it, you're gonna put electrons on it. And I mean on it. Like skimming the outside. They just hang out here, clung to it. Because, well, the electrons, the valence electrons that bond, well, they're just as good to hang out with as any of them on the middle, and they're a lot closer, and they take a lot less energy to get to. And this is something that all conductors do. Conductors take energy and transfer them very well. So they don't take the energy inside of them, they just hold it on the outside. It's kind of like the difference between if you're carrying, like, if you're holding a bunch of water bottles for runners to go by, you don't want the runners to have to dig into your bag to get the waters. You want them on the outside where they can easily get to them and take them fast. Well, that's what insulator, or that's what conductors do. So copper, gold's a really good conductor. Basically most metals, and there's like a line of demarcation on the periodic table, but I don't know it and you don't have to know it. But metals, conductive metals are chill like that. They're trying to hand out waters. On the other side, you've got insulators. And this is like, carbon's an insulator because it's non-conductive. Aluminum, insulator, technically. Not really, it's very poor conductor, but that's a line in the sand we don't have to get to. Plastics, poor conductors. They're insulators. Styrofoam. If you've ever rubbed two pieces of styrofoam together, you'll understand. Insulators do not keep electrons on the outside. So if you hook up a wire to an insulator, those electrons are going on the inside. They are just packing up in here. And you know what? If you give it a place to go, it's gonna let them out. It's not passing them along continually. It's storing them up until there is no other option but to get rid of them. And that's what this dielectric is doing. This dielectric is, just think of it as plastic. And this plastic, or this styrofoam, is just storing up electricity until you give it somewhere to go. And it's going to keep doing that as long as there is a voltage source pushing electricity on it. Hello, welcome. Please mute and until you have a question, and also make sure to double click my screen so you can see it big. Alright, so this dielectric is some plastic or styrofoam or whatever material that is holding electrons. And this is why it takes time for a capacitor to fill up. We all saw the homework problems where it was like, T equals this, and at T equals this, how much is left? And it's like, why does it take time to fill up in the first place? Why does it take time to empty? It is because of the material property. And basically, that's why we say, this circuit has been connected for a long time. Because a long time means that this has had enough time to actually fill up. Because this isn't a fast process. It's not like instant. You can't just put a car battery on a piece of styrofoam and say, whoop, it's full of electricity now. It doesn't work that way. It takes time for the electrons to kind of filter in there and get trapped. So a long time means the capacitor has had a chance to charge. You don't need two C's in capacitor. So the capacitor has had time to charge. So that's like plugging your phone in, or making sure your laptop has enough battery. It's even how the alternator in your car refreshes your car battery so that you can start it. And that's why if you haven't driven in a long time, you need to go start your car and let it run for a little while. Because your car battery and everything else, they are capacitors. They need to be filled with some voltage source. Oh, and by the way, just before we scroll past this, this is the positive side and this is the negative side. If you see this, that means that the capacitor, it matters what direction it's going. So you are only getting you're only getting current this way. You're filling it from this side and it is releasing from this side. Alright. So that's capacitors. And capacitors have specific equations that you need to understand. So the current of a capacitor is the capacitance, which is how much charge can be shoved into the dielectric, basically. It is a capacitance times the change in voltage with relationship to the change in time, or dV by dt. I do insist on saying change in, because that's what a derivative is. It's the change in something with respect to the change in something else. And I do say this in my head every time I write a derivative. So, sorry. Alright, so the voltage of a capacitor, the cap, so that is kind of a uglier sentence. So it is 1 over the capacitance integral from some time 0 to some other time forwards in the future of I of some time d time plus voltage t equals 0, or whatever your initial time is. T0 is not always 0 seconds. Sometimes you're told that this circuit starts at t equals 1. Whatever this circuit starts at, that is t-aught, or t0. And then we have what's actually important to know about a capacitor, because this is the thing that dictates that you will actually practically apply if you ever have to deal with capacitors. And that is the energy. So the energy stored in the capacitor is 1/2 C capacitance voltage squared. And this is energy stored in the capacitor. And you'll notice that it's W, which we used for work. Well, that's because work is the use of energy. Well, this energy isn't being used. This energy is what's going to allow us to do stuff. So it is in fact work. But we phrase it as the energy stored in the capacitor. This is the capacitor's, forgive me, this is the capacitor's capacity to do work. And this is why I hate math, because math is specific words that mean specific things, and they're the only ones who get to use them, as if we don't have a device in our field called a frickin' capacitor. Anyway, my rancor aside, this, if your Newtonian physics is fresh, or if you're a mechanical student and you have to deal with kinetic energy pretty often, this is gonna look really suspiciously familiar, because this is analog to kinetic energy. Ke equals 1/2 mv squared. Well, v is velocity, v is voltage, mass is the characteristic value of some object. Well, capacitance is the characteristic value of a capacitor. And yeah, so just things are self-similar. So energy, not really something you're gonna need to know, but I don't know, I think it's interesting. So we say that capacitors drain continuously. This means that moment to moment, this capacitor is losing voltage. So it's got this much voltage on it at t equals 0, and as t increases, it goes to 0. And it might be a linear relationship, it might be exponential, but either way, there are no gaps. It doesn't go piecewise, stepwise. It also doesn't do stair steps. It is continuous, whether it's linear or exponential. And honestly, this class is only going to touch linear capacitors. That's not true. But either way, linear or exponential, which is going to be the e function, it will decrease continually. But it will only decrease when it doesn't have a voltage source on it. So you saw these circuits that were like, and I should put a resistor there for good hygiene. So we've got some resistor, we've got some capacitor, and then we've got this and some resistor. So we saw these kinds of problems, and it'll say at t equals blah this will open up, or your textbook really liked at t equals blah this will close, which did not please me. So while this side is connected, actually this doesn't make any sense because that's not going to change anything. This will move up to this side. So while this side is running, this capacitor does not let energy through. It does not let current through because it is storing up every little electron that's sent its way. But as soon as this flicks up, as soon as we are looking at, and then this is disconnected, and then this is connected to here, and then we got this capacitor. As soon as we have this capacitor starts draining. Because it is running this resistor, whatever this device is. This is, a toaster. This is your, I don't know, this is your laptop going off of plugged in mode and onto battery. This is, maybe it's the, your radio's fallback when it loses power. Whatever it is, this device is suddenly getting power, but it's getting it from this capacitor, and this capacitor will spin it. So that's why you have to replace your batteries in your devices every now and then, or why you have to charge your rechargeable ones. And it decreases exponentially. Or more, it decreases continually. So up here we said that current did not pass. So what this translates to when you're analyzing the circuit is on DC when connected to a source, capacitors, there we go, capacitors act like an open circuit. An open circuit means there's a gap here. Insert Bug's Life, there's a gap in the line. Nothing you can do. Current's not going to pass through. What it is that this has basically infinite resistance at that time while it's filling. While it's filling, this material has properties such that it just sucks up all the electrons and it won't let any of them out until it is no longer receiving electrons. So as if it has infinite resistance. I have actually done this, and I think it's a funny little short experiment. If you have a breadboard and a battery and an LED and some resistors, which you can get a small kit for pretty cheap on Amazon if you really want to. But all you do is you take the biggest resistor, like some 10K resistor, and you plug it up in front of an LED, and then you attach your battery, and then you just keep adding resistors until the LED goes out. You have created what is effectively infinite resistance. You have created a resistance that is so great that the current can no longer flow through it. It's just funny to see, because you can math that. You can math that very easily. You can calculate if you know that this LED has a current needs a current of 5 amps. You can calculate how much resistance you will need to just absolutely cut off that LED. But doing it on paper and seeing it in action, 2 very different experiences. It's much more fun when you have the devices in hand. Alright, so that's capacitors. Oh wait, we do need to talk about how to find equivalent capacitors, because this isn't... So, we know that resistors behave in series. You can add them up. And in parallel, you have to pray to the gods of inverse numbers. Because you've got R, and you have to do 1 over R plus 1 over R equals 1 over R EQ. So, flip it turn ways for capacitors. For capacitors, these are the ones that are 1 over C plus 1 over C equals 1 over C EQ. And these ones are C plus C equals 1 over C. No. Don't just copy what you're seeing, Ginger. Okay, there you go. C plus C equals C EQ. So, this is how the battery plates and all the toys you had growing up are made, or all of your whatever devices you have now. The battery plate has little nubs for the positive side and little springs for the negative side, and you plug them in like this, and these plates are connected. That's why we call them plates, because this is just a hunk of conductive metal. That's it. So that's my best way to remember which one of these is which, because if this is going to be in a commercial device, it's going to be the easiest way possible, because that's how you make things cheap. So you just add them in parallel. Resistors, you add them in series. So that is capacitors. So one last thing, which I forgot to mention, is the instantaneous power, which you may have to deal with. So the instantaneous power of a capacitor is C, the capacitance, voltage times the change in voltage over the change in time. This should look very, very familiar. It is literally just V times C, I capacitor. There we go. It's I cap, which we had above. See? So, I'll go ahead and summarize, or at least rewrite the equations you need. So, I for a capacitor is C dV dt. V for a capacitor over time is 1 over C integral of t beginning to t end I of time d time plus v t beginning, and instantaneous power. And instantaneous power is literally just, this is it for that instant, for that moment in time. So everything you're doing on DC is generally instantaneous. Everything you're doing on AC may or may not be instantaneous. Usually it's not. Usually you're looking at the whole function. So, this is V, C, dV, dt. Alright. So, after capacitors, we got inductors. And inductors are, if we thought capacitors were weird, inductors are the worst. It's the squirrely bit. And they are weird devices. So, have you ever taken a nail and, this is a loaded question. Have you ever taken a nail and wrapped a wire around it and then plugged it up to a battery and then picked up every metal object on your floor, like paper clips and stuff? That's an electromagnet. That is a property of conductive metals and moving charge, which is electricity, which is current. So what you have is some core. And we in my explanation, that was the nail. So we've got some conductive thing. And then we've got a wire wrapped around it. So I'm just gonna crudely draw a bunch of loops around this thing. So we've got a wire and this conductive metal core. And we've got electricity running through this. So we've got electrons moving around this. Well, cool. What does that mean? So we know that electrons moving creates current. But current has magnetism attached to it. So this is a graphic from one of the textbooks that physics uses, where you've got electricity going in one direction. You've got your current moving. And 90 degrees from that, you've got magnetism moving. And we talk about that as a magnetic field. So basically, whatever, and this doesn't quite make sense, but we're gonna say it anyway because it's the truth. And it's kind of necessary to know for any of this to make sense beyond just, okay, sure, I'll use this. So we have current moving. Just by virtue of current moving, it has a magnetic field going around it. And that magnetic field is going along whatever wire the electrons are moving in. So it is actually going perpendicular to that current. So if we've got a stream of electrons going through this wire, then at every point there is a magnetic field coming up at 90 degrees. So it's called the right-hand rule. And basically, your thumb is the direction of the magnetism, where your fingers are wrapped around the cord. And you rotate it around, and whatever direction that's going, that pushes the magnetism out. It's kind of a hit or miss metaphor in my experience, but it is an important one because right hand rule shows up in a lot of places. So we've got electrons moving around this, and we have a magnetic field moving around each coil of this, or each loop of this coil. So overall, we've got magnetic field coming like this, and that's what picks up the paper clips when you wrap a wire around a nail and plug it into a battery. But each one of these loops is also got magnetic field lines going around it. This is where the inductor stores its electricity. And inductors are meant to be used on alternating current. They're not really meant for direct current. However, we're going to teach them on direct current because it's simpler. And it gives you a place to start. Because if we just threw you into AC and then said, oh yeah, by the way, DC is a snapshot of AC, well, you did all the hard stuff on the front end, and we could have made it easier by starting you at the snapshot and moving out, which is what the class does. So basically, these electrons go through it, and these electrons are going through on DC or on AC to create this effect. On DC, it doesn't really matter because there's no down, so there's no reason for the current to go backwards through it. Basically, when you're pumping a AC signal, so an AC source, through an inductor or through anything, what you are effectively getting is, so you've got this AC source in this really pointless circuit. So when it's on these positive, so if this is positive voltage or whatever, when it's on these upside of these loops, it's going in one direction. And when it's on the downside of these loops, it's going the other direction. So what you have is electrons going through this wire in one direction, and then the other direction. And those electrons are dragging a magnetic field with them in one direction when they're going one way, and one direction when they're going other way. Well, that magnetic field is dragging electrons inside this core back and forth. And it is that sloshing back and forth that stores electricity. Or not stores electricity, but stores energy. It stores it as magnetic energy, basically. Which you don't really have to know, other than it makes this a lot less of a black box if you understand that it is doing something. It's doing something to that core that is distinctly missing from the circuit symbol. So, and it only does that on AC. On DC, all you have is electrons going in one direction through a wire around a core. And while it does create some amount of magnetism, it does not create it to the degree that an inductor is designed to. So, as a matter of fact, on DC, an inductor is just a wire. It's a pointlessly long wire, but it's a wire. So we call it a short circuit. So I will write down here. On DC, an inductor is a short circuit. And what a short circuit means is it's just a wire. It's just a wire. So whatever's on this side gets transmitted to this side without any loss or resistance or anything, because we've assumed ideal. Basically everything. So inductors also have very specific equations that describe them. So the voltage of an inductor, and we've already used both capital and lowercase I in electrical engineering, so we use L because that's good enough, right? Yeah, so if I ever write l'inductor, that was a mistake I made a long time ago that got stuck in my head. So, yeah. VL for the inductor is L, the inductance, which is basically a property of the core material and how many loops of wire are used to create the inductor. And it relates to how much energy can be stored through sloshing electrons back and forth through magnetism. It's something that you have to be given, or you have to be given the parts of, and I'll give you the formula for inductance in a minute. But for voltage, it's the inductance times the change in current over the change in time, where the inductance is the number of turns or loops of wire times mu, which is the permeability of the core. So that is basically how the magnetism behaves with this specific core material. A, which is the cross-sectional area of that core, all over L, which is the length of the core. So basically this is deeply reliant on the device itself. So each model, each brand is going to have a different inductance, but it is something that is A, generally constant with the device in the circuit, and B, you have to be given, or you have to be given a stupid amount of variables. And if you are given this many variables in a question, you kind of got an idea that something might be up. So I'm just gonna describe this because I'm gonna give you these as well, though these notes are not as orderly as the other ones I posted. So this is the number of loops of wire, and this is the permeability of core. And again, permeability is a material property. It just means how are electrons able to move through the core. If it's got a low permeability, then it's not going to be a very good inductor core. If it has a high permeability, then the electron's going to go for days, just all the way through it. So this is the cross-sectional area of core. And when we're looking at the core, this is the cross-sectional area. It's this stuff. And then this is the length of the core, L. So L is completely defined by the device itself. So you have to be given that, or you have to be given 4 variables, or, you'll probably be given diameter or radius, and you'll have to calculate A too, because if they're gonna do this, they're just gonna be rude. So on top of that, we have instantaneous power, P inst, which is still on the V times I equation, but this time it's VL dL di by dt times the current going through it, because current defines what's happening. Current is what moves the electrons. And finally, the stored power, which is the work it could do, the possible work, which is 1/2 Li squared, which also looks like kinetic energy. Again, I'm not driving at anything with that, but it's just something to be aware of. So inductors, once they get going, so again, inductors, there I did it, l'inductor. Inductors and capacitors take time to fill with energy. So, to charge. So, while capacitors will drain instantaneously, once you get an inductor going, it's not likely to stop. Like, it will not take change easily. So, inductors are stable. What this means is that they are resistant to change. They are not really likely to the current is not likely to stop going at that speed once the inductors spun up. Current through an inductor is resistant to change. So that's the one I would write down. So inductors are just like resistors. When you add them, when you're trying to find an equivalent inductor. So equivalence, so if you've got these guys in series, then you just add them. LEQ equals L1 plus L2. And if you have them in parallel, we pray to the gods of fractions and say 1 over LEQ equals 1 over L1 plus 1 over L2. I'm going to write this in a different way, but I want you to remember this one. But anytime you have this situation, so with parallel resistors or series capacitors, you can also say LEQ equals, let's see, it's going to be L1, L2 over L1 plus L2. What this is finding a common denominator in this form and then taking the inverse of both sides, happening all in one step. So that's why I want you to, unless you are very, very comfortable with this, to write down and memorize this form of it. It is much more reliable to just run through the math rules you already know than try and remember something arbitrary and maybe not fully understand where it came from. At least in my experience. I have had a long, hard road with math. So, those are our new circuit elements. And as you can see, they're both only have derivative forms. This is just because of the concepts and rules of physics and math that govern them. There's nothing we can do to simplify them down. I mean, I guess the odd chance of if you were given a distance in time and how the current changed, then you could plug those in straight, but that's not likely to happen. So these are all derivative equations. And so that leads us into the next concept, which I'm so sorry are differential equations. So before that, do we have any questions or requests? Which would be in series or in parallel. So I'm not certain I understand the question I was PM'd. Would you mind elaborating? If you'd like, I can write all three devices right here. So, equivalent devices. So, parallel and series. So for capacitors, if you have capacitor C1 and C2, CEQ is going to be 1 over CEQ equals 1 over C1 plus 1 over C2. And in parallel, if you have this, then you want CEQ, then you have equals C1 plus C2. And then if you have inductors, you have series inductor L1, series inductor L2, and you want LEQ, then you have LEQ equals L1 plus L2. And if you have them in parallel, L1 and L2, and you want LEQ, you have 1 over LEQ equals 1 over L1 plus 1 over L2. And then resistors for good measure. Resistors in series, REQ, R1, R2, REQ equals R1 plus R2, and then in parallel it's going to be just like above, R1, R2, REQ, 1 over REQ equals 1 over R1 plus 1 over R2. Alright, so hopefully that answers the question. If it does not, please let me know and I will look again. Alrighty, so oopsie, hold on. Screen real estate management. Alrighty, so okay. Okay, good. Excellent. As long as I have not created more confusion, that is my primary goal. Alright, so if there's no questions on that, and if I haven't droned everyone to sleep, I will go ahead and move on to first order circuits. Again, I'm so sorry. These are absolutely first order differential equations. And oof. Just oof. Let's see. Sorry, I was just checking the rest of the chat. I will post the notes that are coming with this online as well as the video, so that anyone who isn't able to make this but wanted to will at least be able to see it. Alright, so here we go. We're not doing too bad, actually. First order, time-wise, I mean. First order circuits. These are first order differential equations. So I'm going to take a step back. I know that I didn't take DiffEq before taking this class. This is, what, a sophomore level class? This is a 200 level? So I don't expect anyone here to have taken differential equations. I also somewhat expect y'all had the same reaction I had, which is differential equations, that's the math that the smart guy character does on TV. That's not people math. That's made up. I'll never do that math. You'll do great. If you have to do differential equations, you'll do great. So the first, I'm just going to do some, just make some simple notes for what we call ordinary differential equations. They're basically all ordinary, and by that we mean, I don't know why they call them ordinary, but this is the standard. If you've never seen ODEs, ordinary differential equations, 1, don't panic. I'm serious. That's literally the first step, is don't freak out. Don't panic. It'll be okay. I promise. 2, the goal of first order diff EQ is to be able to integrate both sides to solve it. And that means we have to have a differential on both sides. Which, I mean, that's fine, because we've seen everything in differential form so far. Everything has a differential form in general. So, cool. Cool. So, the third thing is, we have to remember that the form of a derivative is a fraction. It's not an operator. So when we're taking calculus, we see, oh, d by dt of x equals the derivative of x with respect to time. So, you know, whatever this function x is, well, actually that'll just be 1. No, it'll be 0 because there's no t. So d by dt of t is 1 because there's an invisible coefficient 1 here, and then you divide by one of this. Great, cool. That's not an operator. It looks like an operator, and it's taught like it's an operator, but like, you know, the same way that multiplication is an operator or the divisor is an operator. No. Unfortunately not. This is dt by dt. The operators are here, because this is a fraction, and these bastards. Thus, you will never see d as a variable in differential equations. Because d means the change in. The change in what? Well, whatever the letter next to it is. With respect to what? Whatever's underneath the fraction. Thus why I keep speaking this weird combination of letters as the sentence, the change in whatever this is, with respect to the change in whatever this is. Because it's a sentence. This is an arcane sentence. I would like to have some words with math in general. But then again, if I had to write the change in this with respect to the change in this equals all out in words, then it would take even more paper. So, you know, maybe it's a trade-off. Who knows? So 3 is, remember that you can treat the derivative, I misspelled that badly, relationship like the fraction it is. So, honestly, these 3 rules, and don't panic's a very important one, I'm not joking, these 3 rules are all you need to solve first order, so the very simple differential equations. You don't need anything else. So, with that said, let's actually look at what a first order circuit is. So, we're looking at RC circuits. RC circuits. So this is a phrase you can actually Google and get answers. If you type in RC circuits into Google, you'll get videos that are exactly what you're looking for. This is a known phrase and a name of a certain type of circuit. So I guess just keep that in your bag of tricks if you ever have to do this again. RC circuits are literally circuits with an R, a resistor, and a C, a capacitor. So, and we're gonna ground it here. Because we can. Because you can ground it. And also because circuits are grounded generally. So, we know that there's going to be some voltage across this. And that voltage is shared because these are in parallel. And that's how voltage works. So, we also are going to say there is some current and work and kind of go with me on this, because I know that everything we've done up until now says that, well, I mean, logically speaking, there's one current going around this, because that's how current works. But we're just gonna go with this for the moment. So also so this is going to be IC. So each element has a current. Technically speaking, each element does have a current going through it. It's probably the same current. And if your gut is saying ding ding ding, there's a flag here, I should be feeling something, you're correct. If not, don't worry about it. This is literally a shots downrange kind of thing. This is how many times have you done this, and y'all have been doing this for 3 months. Okay? Y'all have been doing exceptionally well. You cannot master anything in 3 months. No human can. And you guys have been doing an exceptional job. So don't take anything that I'm saying as oh well, you're not doing it good enough. You are doing fantastic. These are human limitations. So anyway, if we say that these both have a current, and we're gonna apply Kirchhoff's current law here by saying these two are definitely gonna add to 0, and by gut instinct they should add to 0. Yes. So 0 equals IC plus IR. Well, see, we know these. We found them above. Or at least we know this one was above. dV over dt plus IR. Well, that's just, we're just gonna rearrange Ohm's law because we got R and we got V, and we're looking for I. So we got V over R. Shui. So, that's it. They're very simple, but they are differential. It is a differential equation. It is a differential equation because there is a differential here. Derivatives are differentials. Differential equals derivative. And the word differential comes from the fact that it is the change in V over the change in T. So there are changes. There is a difference differential. So, and I know I'm driving this home like a kindergarten teacher, but these were not so intuitive logical jumps for your TA years ago. So I just want to be clear. So what are we gonna do here? If we don't have values, if all we've got is numbers, well, first of all, we're gonna rewrite it down here over dt plus V over R. So we're gonna go back to our important rules of first order differential equations. We have not panicked, so we have finished rule 1. We've girded our loins, and we have squared our shoulders, and we have started. That was the important first step. Step 2 is remembering that the goal is to be able to integrate both sides. So we gotta get that into a way we can integrate both sides. So how we gonna do that, boss? Well, it's real simple. We're just gonna pull one of these terms to the other side. Sometimes you might have to do more and more finicky algebra to get this into this state, so that's why I stated it as be able to integrate both sides. So basically, we're gonna say C change in voltage over change in time equals negative V over R. We've just subtracted this to the other side of the equals. So now we're still not ready yet because we can't differentiate both sides yet. We have a change in V term and a change in T term on the same side, and you can only integrate by one variable at a time, and we can't double integrate this side and not integrate either times this side. So what we gotta do is we are going to cross multiply. We're gonna leave the C alone. The C can stay. The C is not really related right now. So we're gonna hold this C No, I'm sorry. We are actually going to attach that C to well, we'll see how it goes. So we're gonna cross multiply. We're gonna get this junk on the far side. So we need that V term to be on the same side as this dV. That's the only thing that really, really has to go in a certain direction. Because they share a term. They share a variable. So we're going to multiply this, or divide this V across. So we're going to have we're not going to write with the highlighter. We're going to have 1 over V, C dV over dt equals minus 1 over R. And I'm going to do this the really long way, and I know it's going to be annoying, and I'm sorry, but I feel like it is necessary to not skip steps right now. So the next thing we're going to do is we are going to multiply this dt over. We got 1 over V dV equals minus dt over R. Cool. We still have this C over here, and we don't really want it. It is in our way. So we need to get this over there. So we're going to divide it across. So we've got 1 over V dV equals minus 1 over CR, or, you know, RC, like the name of this kind of circuit, times dt. And you notice that I pulled this off of the fraction, and it's just because it makes it a little more obvious what we're going to do next, which is we go integrate. We're going to integrate both sides. We did it. We made it through step 2. So we're going to do that. We're going to integrate both sides. And when you integrate, you are integrating with relation to this variable. So you only need to think about the stuff that is coefficient to that variable, which is fine on this side because we got a 1 as coefficient, but we do have this in a fraction. So that's fine. That's honestly fine, because the integral of 1 over x is the natural log of x. So this is ln of v plus c. Yeah, we'll deal with that later. We'll deal with the plus c later. But this is ln of v right now. And this baby, well, minus 1 over RC are constant. That capacitance isn't changing. That resistance isn't changing. That negative is negative. So minus 1 over RC, integral of dt. Well, this is actually integral of an invisible 1 dt. So we got ln of v equals minus 1 over RC t plus c. No, we're not going to use c. Okay, so in math, it's usually plus c is some constant that represents the uncertainty, because this was an indefinite integral. For obvious reasons, we can't use c, so we are instead going to use the letter a. So, sweet. Now we have something useful. We have just done a differential equation. So now let's just get it cleaned up, because, you know, it doesn't really mean a whole lot. It's not very meaningful right now. We don't really know what this means. So, especially since the variable that we can kind of solve for, because, you know, Ohm's Law is defined, is literally the definition of voltage. So we're gonna focus on voltage because that's kind of the core of our entire field. So we're gonna cancel out that natural log, and we do that by raising both sides to the power of e. To the power of e. There we go. So that means that to the power of e as well. Yes, that is correct. So we've got that cancels out, so we got v. Sweet, we got v. We have we have me losing my place in my notes. I apologize. 1 second. Oh, right. This A was actually part of that side. So, this is also plus ln of A on this side. That is what I did wrong. So, let me just go back a step so that I don't leave question. So we're here and we are doing this integral. This is ln of v plus ln a. This happens just because it's a rule of integrals. That's how this works. Equals, this is minus 1 over RC integral of dt. And like we said before, there's an invisible coefficient 1 next to this dt. There's 1 dt here. I know that's a stretch, but it is the truth. So this becomes minus 1 over RC times t. And then we've got these natural logs over here. So we're going to go ahead and move this ln of a across. And we're not really going to pay much attention to the sign of this of this ln of a, because this a is a constant, but is an unknown constant that we have just thrown in there to account for the uncertainty of this integral. So it's going to absorb the negative so we don't have to look at it. And that's a valid thing to say, specifically about this tacked on extra constant that happens with indefinite integrals. It's shenanigans. It's absolutely math shenanigans, but we're allowed to do it. So we're going to say ln of v equals minus 1 over RC times t plus ln of a. And then we're going to raise both sides to e, or we're going to raise e to the power of both sides, which is the only way you can get rid of ln. So we've canceled out ln. It's 2e, and by the way, this, even though we've done it to the whole term, the way e evaluates, this side stays raised to the power of t over RC, but the ln here is canceled out, so we just have a. Cool. So, Actually, I've done things in the wrong order again. Again! Oh, this stuff is very, very specific, and it has admittedly been a little while. I apologize for these errors. It's... Alright. We have this ln of v. We have this plus ln of a. We're going to subtract that ln back over. Why are we doing that? Because that gives us ln of v over a equals minus 1 t over rc. Then we raise e to the power of both sides. So we've gotten rid of the ln. We have v over a. We have e to the minus t over rc. We're going to multiply this a across. And this is a standard form of voltage. So this is the voltage of a first order circuit, of an RC circuit. That is not the pen I meant to use. And you can just use this equation. You don't have to do the differential equations. You can just use this. Alright. So, done with that page. Alright, so this equation represents, and I'm going to write it down because this is kind of important. So this equation represents the voltage of the capacitor. As it decays over time. So this is what we were talking about before, that capacitors drain continually. This equation is an exponential decay. This is the same form that if you've ever had to do the how long will it take for the bathtub to drain problem takes. It's pretty standard, where this is the time constant. And we represent time constant with tau. There we go. Tau. I see it as Japanese character te. And had to change languages. So this is the time constant tau. And this is the form the time constant takes for RC circuits specifically. So this equation, again, is the voltage of the capacitor as it decays. That was not a good color to use. There we go. So the RC basically represents, please change to the right. RC represents the time it takes to degrade by a little over half, to degrade by 63.2% of the capacity. So that's probably not gonna be directly useful to you, but just understand that this time constant is basically the half-life of the capacitor. If you understand, like, radioactive materials have a half-life. They degrade by half after a certain period of time. This is, the RC is basically the same thing. It is roughly half of the capacity has been drained by this time. So it's roughly here. RC on T. So, cool beans. There's some equations that you probably want to write down. So, the current in an RC circuit is a function of time. It is the original. So whatever you started with. It's not necessarily V at t equals 0, but it is V at the beginning of time for the circuit. Over R e to the negative t over RC. And power of an RC circuit is going to be V aught, which is, again, just the first voltage. Initial voltage over R, e minus t over RC, times V initial, e to the minus t over RC. So this V initial, by the way, is this random constant. So this constant basically translates to being the initial. So, and this is still the form of power equals VI, and simplified down it becomes V aught squared over R times e to the minus 2t over RC. And I will highlight that one because that's the one that you probably really want. And then finally we have the work. So the stored energy, or in this case the energy absorbed by the resistor. So work of an RC circuit is also a function of time, because everything else here is a function of time. From whatever t initial is to t, it might be 0, it might be 37, but whatever it is, it'll be stated. Or if it's not stated, then it's 0. Power is a function of, and we're just using x here because it's just the x-axis value. Because this is a definite integral, you're just going to replace it with t, so it's just going to become t. Which comes out to being 1/2 capacitance initial voltage squared times 1 minus e to the minus 2t over RC. And you'll probably want that one, this version of it, written down as well, because I certainly don't want you to have to live do an integral on an exam. Dr. Doss doesn't either. Alright, so those are RC circuits. Then we have RL circuits. So in essence, you've changed the method of storing energy in the circuit. So RL circuits. Oh yeah, absolutely. Here we go. Okay. No problem. That is very important. Alrighty. So select the thing I want you to select. Okay, so if we move on to RL circuits. So this is basically the same situation, except we've replaced the capacitor with an inductor. So we've got squiggly boy here, we've got a resistor, and we're gonna ground it, because grounding it makes the brain happy. So we've got L. Actually, I'll just keep it all consistent. L. And we say that it has this VL minus plus. And we know that there's some VR across this, plus, minus. And we know that there's a current going around this. So we're going to find the sum of voltages here. So you might notice a pattern where we look at sum of current for because it becomes in terms of voltage. And voltage is associated with capacitors. Current is associated with inductors. This is just because of how they work. It's because of how they're designed, how they're made. So we're going to look at the sum of voltages here because we really want to be talking in terms of current. And we want to be talking in terms of current because we're looking at an inductor. So we're going to say 0 equals, well, we're going to come into VR on the positive side here, VR, and well, we've very strategically come into the positive side of VL because we decided to install that one upside down so that this would work, VL, and we're gonna write those in terms of their current and main property. So for the inductor, it's gonna be L di by dt. And for the resistor, it's going to be R I. Sweet. Okay, cool. So we're going to follow the same steps, and I'm not going to put you through the derivation of 2 first-order differential equations. It follows the same steps. Don't panic. Don't panic. Get it into a state where you can integrate both sides by putting one differential term on each side and grouping like terms, and then make it pretty so that you can actually understand it. So solving this ODE, we get I of t, because it's going to be a function of t, equals I out, or I'm sorry, I initial, so it's the basically I0, times e to the negative t r over L. And in this case, r over L is the time constant. It's actually L over R. Tau. It's inverted here because that is effectively minus t over tau, which is minus t over L over R, which becomes tr over L. So that is what's happening there. But in essence, time constant, L over R. You probably need to know how to calculate the time constant specifically. That's usually a common homework question and stuff. So, and we get the same, we get relationships for these as well. So we know that if we have a specific current, we've got a specific voltage, we've got a specific power, and there's probably a specific work stored energy value, especially since the whole point of an inductor and a capacitor is to store energy. So we're just going to go ahead and write those down as well. So we have, if we have this current, so I'll just write it down here so that it's all together. That's an I, because I write them very, very poorly. And I'm going to write this like this. Then we have voltage of an RL, which is also a function of time. It's I aught e to the minus RT over L, which is the same as this term, just not expanded. We have power, which is going to be the instantaneous power. No, it's not. It's going to be the power of the whole function. It's a function of t. It's I aught squared times R times e to the minus 2 RT over L. Because it is, again, it's that I times that R to make that power. And then the stored energy, which is the work, is from the integral from some initial time to some ending time of P of t dt, and that comes out to being 1/2 L I aught squared, so initial current, times 1 minus e to the minus 2 RT over L. So those are the important values for a first order circuit that has an inductor instead of a capacitor. Alrighty. And I'll give you a minute to be able to write that down so I don't zoom past it again. We're also going to look at second order circuits, which is going to take just a bit longer. Okay. So, but good news is we're mostly through. Alrighty. So if we are good to move on, if there are no questions or anything, just checking Discord real quick. Alright, so we'll go ahead and move on to second order circuits. And I won't derive a whole second order differential equation, because that'll eat up the rest of our time. But second order circuits are characterized by second order ordinary differential equations. So second order differential equations have double derivatives in them. So we're talking about things that are dx squared by d squared t, or something like that. This is what tells you it's a second order differential equation, because so exponents define the order of a polynomial, and this is where we find that in a differential equation. So what this effectively means is there's two forms of energy storage in the circuit. There are two forms of energy storage in the circuit. And to put that bluntly, we only have two forms of energy storage that we know of. We've got inductors and capacitors. So we got them both. AKA both inductors and capacitors present. So what that means is a circuit kind of like this. We got some resistor, we got some inductor, we got some capacitor, and nothing else. And that's fine. We really don't need a voltage source on top of this to make this more complicated. We're basically using these very simple situations to derive a standard form that will advise the way we move forwards in more complicated circuits. So we've got this V initial. So we're going along the assumption that this has been charging for a while, that both of these have some charge. So we've got an L, we've got an R, we've got a C. Hello, welcome. I, got plus minus, just for our reference. And by the way, we've got an I out, or an I initial. We have both a voltage initial and a current initial condition, which is important because they are important for different elements. We need the current for the inductor, we need the voltage for the capacitor. If we don't have these, we can't really solve this. So we've basically created a situation that we can solve. So we're just going to go ahead and say it. We're going to assume L and C have been charged. So they're full. They have power. They are storing something. They're not empty. 2, we're going to look at time is equal to 0. So basically pre-start time. What that means is anything could have happened before t equals 0. But all we care about is whatever that was. Is the beginning of time to t equals 0 when the circuit starts. Dinosaurs roamed the earth, and we're gonna look at that. So we're gonna say that at time equals 0, the voltage of 0, of t equals 0, equals 1 over c minus infinity to 0. So again, we're looking at anything that could have happened ever before 0 up to 0 of I dt. And we recognize this. This is the voltage of the capacitor, which is V initial, which is the voltage initial condition that we need. So we're just going to look at that, and we're going to say that that is V aught, V0, V initial. And then we're going to say that I of t equals 0 equals I of 0, which we were given. We don't have to do anything funny. So, and again, we chose negative infinity because we don't know what happened or how long this has been charging, but we assume that it has been charged. So we gave it all the time in the world to be charged. It is at capacity, whatever capacity is. So that's why we choose negative infinity. So the next thing we're gonna do, so these are important mouse tools for later. We need these. These are important mouse tools for later. We're gonna need that. So we're just gonna leave ourselves a little symbol. So we're gonna move on with evaluating this second order circuit. And I'll quickly redraw it so that it's on screen. We've got R, scribble, squiggle, L, C, done, C, we got I aught, we've got V aught, plus minus. Alright, sweet. So we're now going to apply voltage law. So step 3 is apply KVL. And what we're going to get is 0 equals R times I, R times I, and we're purposefully kind of smooth brain just saying there's an I here even though we have one here because we're gonna plug that in later. So we're gonna say 0 equals R times I because that's the voltage here, plus the voltage equation for an inductor, di over dt, plus the voltage for this capacitor, V, hold on, 1 over C, integral of minus infinity, t, I, some variable, d variable, and all of that equals 0. Neat. Okay, cool. So if we were to try and just do this like so if we were to just evaluate this integral first, so that because we can evaluate this integral, it has all its pieces, we could just do that and then use that to simplify it, we would get something of second order, and we're gonna do that, and it's not gonna make us happy people, but we're gonna do that. And basically what effectively we are doing is we are differentiating this whole thing. So we're gonna take this with respect to t, and this, and this. So what we're gonna end up with is d squared I over dt plus R over L di dt plus I over LC. And you don't need to know this, and I don't know that anyone's actually taken differential equations, but this is of form y double prime plus y prime plus y, which is our standard form for a second order differential equation. Double prime just means it's been, the derivative with respect to time has been taken twice. The derivative with respect to time has been taken once. There is no derivative having been taken. So this, in essence, this is a coefficient of I, this is a coefficient and derivative of I, and this is a second derivative of I. Well, jeepers. Okay. Not fun. Not fun. So, I don't know. Differential equations became fun after a while, but you again don't really need to do that. So what we're gonna do is we're going to solve this. We're gonna solve this, but let's look at how to look at second order ODEs, and some of you might have to take differential equations later, so just maybe this will be a primer. They're not really that bad, but oh boy. So, again, don't panic. Don't panic. To, basically, get it into the y double prime plus y prime plus y equals 0 form. And then don't. So basically you're going to then take the original and linearize it. And the way we're going to do that is by basically, instead of, so we need this. Make no mistake that this was a correct move. But we're then going to take this and say, well, actually, this is our initial condition of V aught, so we're going to do that. Yeah, so I here is I ought. So we're going to rewrite this linearized. It's basically, we've taken out its ability or need to be double derived. So then we're going to make it to where you can integrate both sides. Step 4, they get very long, yes. We're going to reformat it into something we can use. You shove that back into the original, into the differentiated form. So basically, back into the step 2 form. And then you're going to simplify and find the roots. And like I said, I'm not going to put you through all 6 steps of this. Instead, we're just going to look at the roots. So the roots of a differential equation are what you're looking for. They describe behaviors of that differential equation, and that's true for all of them. It could be, springs, masses on a spring. It could be electrical devices. But basically, in our case, the roots of our ODE are natural frequencies. Natural frequencies, which define the damping of the circuit. So the roots we get out, wrong page. So the roots we get out are of form S1 was minus some alpha plus alpha 2 minus omega aught squared, and S2, because basically what we ended up with is a second order polynomial, which means we could apply the differential, not the differential, the, well, now my brain's lost it. It's the equation you get to get the roots, so to get the factors of a polynomial. Not positive, negative. So this is going to be alpha 2 minus omega naught 2. And these are important. So depending on how the differential equation went, will define what these roots behave like. So let's see here. Yeah. So, and these roots define damping. Well, what is damping? So, damping is basically, it is how inhibited the circuit is, or the system in general. Because even Newtonian physics, especially mechanicals, will have to deal with damping as a concept. So damping is how inhibited the system is. Inhibited is, well, that's basically resistance. Impedance. How badly impeded is the circuit or not. And we care about this because it describes the frequency of circuits, especially in AC. Mainly because AC circuits oscillate. So they go above and then below 0. Or they, just go between a set of high and low values. It's oscillating. So we care, because, the level of damping describes whether the circuit will resonate naturally without a voltage source or a power source or whatever. Basically, without something externally driving it. So, the level of damping describes whether the circuit will resonate naturally without a driving force. And that's kind of cryptic. But basically it means how efficient is the circuit, how likely is the circuit to grind to a halt fast versus grind to a halt at a period which we can predict. Hello, welcome. And or how likely is it to kind of go wild? Because it's that last one we really need to be aware of, especially in well, basically everything. Because if you can't really predict how something is going in the real world, you cannot control it, or you cannot make predictions, make educated guesses about it. Like, you really don't want the power coming out of the power company to be erratic. That's how you destroy gaming consoles, is erratic power. You don't want the robot arm on your manufacturing line to just by the way the motor is causing vibrations through it to wiggle itself apart, and then you have like careening bolts and stuff across your manufacturing line. So we have to care about this stuff. And in electricity, basically in everything, it's still the same, but for our terms, we're going to define 3 states of damping. So you remember this alpha and this omega aught. So these 2 terms together create the damping ratio. And we call it... Oh, that's not the right character at all. That's not a character. I thought too much about it. So this is zeta. This is zeta, lowercase zeta. And zeta is alpha over omega aught. These terms are... hold on. This is the damping ratio. And alpha equals R over 2L, and omega aught equals LC to the negative 1/2. That is to say, this is 1 over the square root of LC. And these come out of that differential equation that we did not derive the long way. But just trust that they exist. It might do you to write these down, but I doubt you're gonna have to do too much. So you're certainly not gonna have to derive this whole thing. So we're gonna dictate 3 states of damping, and if y'all are good to continue, I will continue as well. It is currently 8 o'clock. So we have 3 states of damping. We have where alpha is greater than omega 0. This is called overdamp. This is a situation where the response decays pretty quickly. So, but it is not in a very predictable way. So it just kind of goes like that. It's roughly shaped like a derivative of the E function because because solutions of a differential equation usually take the form of E or cosine sine combinations. So in this case, I of t equals a1 e s1 t plus a2 e s2 t. There are 2 real roots in this situation, and they are different roots. You don't have to deal with I. The second case is where alpha equals omega aught, and this is critically damp. Crit damp. And this is where I of t equals a2 plus a1 t e to the minus alpha t, and there is 1 real root, but it repeats, so both roots are the same, so omega and a are equal. And then the last one is alpha less than omega aught, which is underdamp. And this is the case where things go wild. This is 2 imaginary roots. So I of t equals... So you're not going to see the I here because this is how differential equations are processed. You process out I by creating a combination of cosine and sine. But again, you don't need to do that until you're actually in differential equations. Omega t plus b 2 sine omega dt. So this is a situation that looks like this. And it's just kind of going to go on forever until, you know, real inertia and real life things make this go blank. This is bad. I mean, there might be applications for this, but if your power is doing this, then you are running some devices through hell. If you have this kind of wave set up in a like a robot arm, then something's wiggling, and it's not really ideal. We usually want critically damp because we can predict it, because it behaves like this. It's reasonable. We know what time it finishes decaying. We know where it halfway is. We know where this is. We can predict it, so we can design around it and we can control it. Underdamp's wiggly, man. Okay, so that is damping, and that kind of brings us neatly into sinusoids. So we are almost done, but we've not looked at sinusoids or phasors. Or technically impedance, although impedance is really just complex resistance. So, how are y'all feeling? There's probably another half hour or so. Oh, you're welcome. Yeah. Okay, yeah, it's 8 o'clock at night. You're welcome. I'm really glad to help. I hope that some things kind of made a little bit of sense. I know I ramble a bit. So I don't have a solution manual for chapter 13. But Oh, 8 and 9. I'm not sure, but I can ask him, and I have solutions so I could also upload those myself. I'm sure it's just something that he hasn't gotten around to. So, okay. Yeah, that's fair. I'll send him an email tomorrow morning. You're welcome. Have a good night. Try and rest up. Alright, I'm glad you're feeling better than yesterday. I'm sorry, I don't know your name other than your Discord name, Forest Fire. So I'll just call you that if that's okay. Okay. Yeah, so I'm glad you're feeling better. So those of you who are still with us, do you want to continue and hear about sinusoids and polar and rectangular coordinates and phasor notation? Because that's basically all I've got left. The rest of it is kind of not stuff you actually need. I was going a little ham on the notes. Okay. Okay. Thank you very much. Alright then. I will go ahead and call it unless anyone else in the chat has other opinions. It's my pleasure. Good night. Alright, thank you all so much for coming and for being great listeners. I will still take your questions over the weekend, assuming I don't see that you've started the exam. Because I can see the gradebook, but I will take your questions until Monday, which is the official start of finals for UNLV. So, alright, good night! Thanks, everyone!